Section 8.2 is on human inheritance. As far as our lesson objectives, this is kind of a long section, so I'm going to split it up into 2 days. Today, we're going to be able to describe inheritance in humans for both autosomal traits and X-linked traits. The other 2 objectives we will get to tomorrow. So, the easiest place to start is with Mendelian inheritance or Mendelian traits. Think back to Mendel, pea color, green, yellow, pod shape, height. There was only 2 options. It was very simple. Well, these are inheritance patterns that are simple. They have 1 gene involved, and that gene has 2 different forms, 2 different options, alleles. And it shows a simple dominance where there's something, a dominant allele and a recessive allele. A couple examples we'll look at is widow's peak, when the front of the hair comes to a point, versus none, and hitchhiker's thumb, with the ability to extend the thumb much greater than somebody without a hitchhiker's thumb. So if something is autosomal, remember our autosomes are the first 22 chromosomes, number pairs 1 through 22, not the sex chromosomes. Some of the traits that are autosomal and are simple Mendelian traits are free hanging earlobes. So a free earlobe will go kind of I should say detached, will go down, and this is all detached. An attached lobe is attached. It doesn't have that extra bit that is free or that is hanging down. Widow's peak, as I've shown again. Speak of the house, Paul Ryan has a very prominent widow's peak, and this girl whose picture was on a Wikipedia page does too. Don't know who it is. And we saw hitchhiker's thumb in the previous slide. This site has a couple other ones. There is some debate over whether these are truly single genes. Not 100% sure, but for our purposes, they sure work for it. Cleft chin is a dominant trait. Not cleft is recessive. The ability to have dimples, cheek dimples, that is a dominant trait. None, recessive. Dominant or free earlobes is dominant trait. Attached is recessive. Freckles on the face is a dominant trait, with none being recessive. The lack of a hitchhiker's thumb is the dominant condition. A hitchhiker's thumb is recessive, and a widow's peak is dominant, while non-widow's peak is recessive. The ones below this are ones that are going to need many genes. They're not simple. They're going to have a wide range. Eye color, hair color, the ability to roll the tongue, and we'll kind of look at some others. Pedigrees. Pedigrees are charts to explain relationships among families and to track conditions or traits over time. First thing to know when looking at these is that squares represent males and circles represent females. And when a male and a female are attached side to side, let's get real, that doesn't necessarily mean they're married, but it means that they reproduced. So here are their children. This man and this woman have 2 children, and apparently they are both female. So let's look at a Mendelian trait, earlobes, among generations. So we're looking at, we'll start at the bottom. We've got 2 siblings, 2 sisters it looks like, because they're circles. One has the detached earlobe, which is, or the free, which is the dominant. and one has an attached earlobe. Maybe they wonder why. Well, attached is going to be represented by purple in this case. So they go back to their mom and dad. So here's dad. Dad has unattached or free earlobes. Mom has attached earlobes. If you look at mom's family, this would be mom's sister. So an aunt. Well, mom's sister, their aunt, has detached or free earlobes. They go back to mom's parents, their maternal grandfather and maternal grandmother. They find that grandpa has detached earlobes. Grandma has attached earlobes. Looking back at dad's side of the family, here's dad. Dad's got two brothers and a sister. One of dad's brothers has the detached dominant. One of dad's other brothers has attached earlobes, the recessive condition. And dad's only sister also has attached earlobes. Looking at dad's parents, the children's paternal grandfather and grandmother, grandpa on dad's side has the recessive condition, attached earlobes. Grandma has the dominant condition, detached or free earlobes. So we can use this to figure out where did those genes come from. For this particular girl, one of the little F's came from mom, and essentially way back to either grandma or grandpa here. Actually, one of the F's would come from grandpa, one of the F's would come from grandma. And the other F came from dad. Dad must have gotten that from his dad. He would have got the big F from his mother. Traits that are sex-linked are on the sex chromosomes, either the X or the Y, but as discussed before, since the X is so much bigger than the Y, it has so many more genes, usually these traits are going to occur on the Y chromosome. What this means is that girls, you have 2 chances, guys, you have 1 chance as far as alleles expressed on your X chromosome. If there is a recessive condition on the X chromosome and a male gets it, it will be expressed. It will happen. They will be affected. If a woman gets an recessive X, just one of them, meaning the other one's dominant, they will not have the condition, but they will be a carrier for it. The only way that a female gets a recessive sex-linked condition is if they have it on both of their X's. So let's say a father that is unaffected, and this could be for any trait. We could be looking at color blindness or hemophilia, which I'll get to. But dad has an X and a Y. Half his sperm get the X, half the sperm get the Y. He has a normal X with the dominant condition. We'll say normal color vision. Y doesn't even have that chromosome or that gene. Mom also has normal color vision, but she carries the recessive X for color blindness. So half of her eggs are going to get that normal X that has regular color vision. The other half is going to get the X that has the little r for color blindness. We'll just be recessive here. So what are their options? You could have this sperm from dad and this egg from mom. You have an unaffected daughter, has both color normal traits. You could have this X sperm from dad going with this X egg from mom. You have a daughter that has normal color vision but carries that color blindness trait. You could have this sperm, dad's sperm, that contains a Y chromosome. This sperm combined with this egg would give you a son that is unaffected, normal color vision. This sperm with this egg, however, gives you a son that has an X for the recessive condition, color blindness. They are affected because they don't have another X to cover it up. The only way that a daughter is going to be affected in this case, they would have to get a recessive X from mom and a recessive X from dad. In order to try to get people to watch crappy Thursday night football games, the NFL decided to do color rush jerseys. Instead of the traditional dark color or solid color and white, both teams would wear solid colors. The first one was kind of a disaster, which they hadn't thought of yet. They had a team that wore all green and a team that wore all red. However, red-green color blindness is the most common, and it's especially common among males, which happens to be their largest audience. Let's take a look.
Because some fans who are colorblind could not tell the two teams apart. Most of us saw a rush of color when the Bills beat the Jets last night in New Jersey, but others didn't. And it's causing quite the debate online. That's because some fans who are colorblind could not tell the two teams apart. Deadspin posting this video showing what it looks like to watch the game when you're colorblind. The league says it will incorporate a color blindness analysis when designing jerseys for next season. Various studies have found that red-green color blindness, is most prevalent and affects as many as 13 million Americans. Most of us saw a rush of color.
Kind of weird. And then hemophilia is the other one that's not as common anymore, but used to be more common in the past due to the way that royal families wanted to only reproduce with other royal families, which happened a lot in especially Europe from the Middle Ages to recently, and that will give you some inbreeding, which can lead to some bad things. Alright, so I want to go through this quickly with you. I will kind of read the quick little story with the pedigree. Her Royal Majesty Queen Victoria of England. There she is. What a cute lady. We shall tell you about pedigrees. Ours is most detailed. We will focus on that part of the family leading up to the Russian royal house, the Romanovs. Wait, didn't you say England? Yes. Most of Europe's kings and queens and royal families were very closely related. So here's Victoria. This little dot means that she is a carrier for hemophilia. Pedigrees are most useful for tracing lineage, and since the mid-1800s during my reign, pedigrees have been adapted for tracking human genetic heredity to find out what the heck is going on. Females are represented by circles, males by squares. A horizontal line connects those who reproduce. They might be married, they might not. And vertical lines lead to children begotten from the marriage. Albert, my dear Prince Consort, and I, that means that's her husband, had 9 children for the glory of England. Girl, boy, girl, boy, girl, girl, boy, boy, girl. To our sorrow, our line was tainted with the royal bleeding disease, hemophilia. Since the early 1800s, hemophilia was believed to be an inherited disease affecting males. I did not have hemophilia, but it seemed that I carried and thus passed the traits to my descendants. In the genetic pedigree, individuals known to be affected by a trait are filled squares, or circles, carriers are dotted. I, Queen Victoria, was a hemophilia carrier. Of our 9 children, poor Leopold had hemophilia. We know Alice and Beatrice were carriers because hemophilia was seen in their male children. Of my grandchildren from Alice, 1 had hemophilia, 2 were unaffected, and 2 were carriers. So here's our carriers, here's our affected boy. 'Twas most unfortunate, my granddaughter Alexandra was a carrier. She married Nicholas Romanov II, Tsar of Russia. They had 5 children. My great-grandson, the heir to the throne, Alexis, had hemophilia. Tragically, the whole family was killed in 1918 by the Bolsheviks during the Russian Revolution. You may be more familiar with the story if I told you that one of Alexis's sisters was Anastasia. Of course, since the whole family was killed, it is not known if any of Alexis's sisters were carriers for hemophilia. They would have to have boys of their own to find out. If you look at our pedigree, only the princes are affected, and some of the princesses are carriers. This, we've been told, is a classic example of sex-limited or sex-linked recessive inheritance. A sex-linked trait is on the X chromosome. Females have 2 X chromosomes. They can inherit/carry the trait without being affected if it acts in a recessive manner. Hemophilia is such a trait. So Queen Victoria would have a normal blood condition and an abnormal hemophilia condition. By the way, hemophilia, you are unable to stop bleeding. You can't clot your blood. It's a bad deal. Males only have 1 X chromosome, so if they inherit the affected X, they will have the disorder, just like poor little Alexis and poor little Leopold. Follow my affected X chromosome through our pedigree. Well, the affected X went there, it went there, it went there, and from here went to there, and there, and there, and there, and maybe down here. Well, hi, Charles. I'm Charles Davenport. In 1907, I published The Genetics of Eye Color. Dark eye colors are inherited in a dominant manner. Light are recessively. I'll show you. Nah, because that's not exactly the case. We'll cut that out. And lastly, I want you to do a pedigree analysis activity on your own. I will post this link